Hello, I'm Arindam Bhattacharya, a PhD student at IIT Delhi. Today, I'll be talking about data-aware hash functions for Bloom filters. A Bloom filter is a probabilistic data structure that is designed to answer the question, is X an element of S? To construct a Bloom filter, we first take an empty bit array of n bits. Then we choose k hash functions, and then we pass the element X that we want to insert into the Bloom filter through those k hash functions. Each hash function maps the element to an integer from 1 to n, and the corresponding bin in the bit vector is set to 1. Let's look at some other properties of Bloom filters. A Bloom filter has this interesting property that it may produce false positive, but it can never produce false negatives, which means if a Bloom filter says that X is an element of S, then it may belong to S, but may not. But if a Bloom filter says that X does not belong to S, then X definitely does not belong to S. Suppose we want to create a Bloom filter such that the rate of false positives does not exceed a certain value epsilon. Then we have this relationship where the size of the Bloom filter n is proportional to the number of elements inserted n and log of the inverse of epsilon. So given this, can we do better? Right? Can machine learning help us achieve a better relationship between false positives and the size of Bloom filters? Well, yes, if there is a pattern in the data. So how we would go about doing that? The construction would be something like this. We train a classification model such that the positive data comes from the inserted keys and the negative data comes from the non-inserted keys. And to ensure that this construction does not give us false negatives, we insert the false negatives of the model into a smaller backup Bloom filter. This structure is called learned Bloom filters. So what are the major problems with LBF that we are trying to address? Well, separate machine learning classifier requires major implementation level changes, and it is hard to replace existing Bloom filters with such models. Next, these machine learning algorithms require several design choices for which there are no theoretical guarantees. These choices need to be made empirically for different datasets. And finally, out-of-the-box machine learning models are not optimized for speed and compactness, and these two are the most desired properties of a Bloom filter. So what is the solution? We propose partition hash Bloom filter, PHBF. Partition hash Bloom filter is easy to implement by just swapping out the hash functions of existing Bloom filter with data-aware hashes. The design choices for PHBF are guided by theoretical results. It uses a novel projection-based model, which is designed to overfit. And finally, it is optimized for compactness and query speed. Let's see how PHBF works. The key idea is to replace the Bloom filter's hash functions with data-aware ones. A PHBF has two construction phases. The first is vector selection phase, where we select k good vectors using the sets x and y. And then the hash computation phase, where we compute k hash functions using the vectors selected in previous step. Each hash function operates on a disjoint partition of the bit vector b, each of size m by k. Hence the name partition hash Bloom filter. So now some results. First, PHBF has this property that the size of PHBF is independent of the number of elements inserted for certain distributions. You can see the proof of this in the paper. Note that this is different from standard Bloom filters, where the size is dependent on number of elements. Next, PHBF improves the FPR by up to 2 orders of magnitude when compared to standard Bloom filters. And it achieves same FPR as learned Bloom filter at 1/3 the space. Also, it is 15 times faster to construct compared to the best performing learned Bloom filter. So in conclusion, we propose a new algorithm, PHBF, that is faster and more compact alternative to Bloom filters and learned Bloom filters. We also show that PHBF's design choices are based on theoretical analysis and not empirical data. Thank you for watching this 4-minute wrap-up.